Yeah, ready, sir. Ready.
Okay, thank you, sir. Okay, today is binomial theorem, class 10, binomial theorem, class 10. In the last class, we have discussed about the numerically greatest terms and the largest binomial coefficients, and we've written the identities, and we have also done few problems based on numerically greatest terms. Today we shall see some more problems. One is based on largest binomial coefficients, and another few problems on coefficients. Okay, so problem number, according to the serial number, it is 24. Find the largest binomial coefficient in the expansion of we have 2 bits under this one. We shall see 2 bits, 1 plus x whole power 19, and the second bit 1 plus x whole power 24. Let us see the solution. First, we'll try to solve the first bit, which is, what is the expansion we have? 1 plus x whole power 19. Here, n is equals to 19. Is an odd integer. N is equals to 19 is an odd integer. Therefore, the largest binomial coefficient coefficients are NC n minus 1 by 2 and NC n plus 1 by 2. NC n plus 1 by 2. That is, what is the value of n? N is 19. So we get 19c 19 minus 1 by 2. So this is NC n minus 1 by 2, which is 19c 19 minus 1 by 2, and (19c) 19 plus 1 by 2. 19c 19 plus 1 by 2. So what are the coefficients we got? it will be 19C, 9, and 19C, 10. So these are the largest binomial coefficients in the expansion of 1 plus x whole power 19. Note that (19C) 9 is equals to 19C 10. We shall take the second bit. You have to find the largest binomial coefficients in the expansion of 1 plus x whole power 24. We have 1 plus x whole power 24. Let us see this. Here, n is equals to 24 is an even integer. Is an even integer. Hence, there is only one largest binomial coefficient. Only one largest binomial coefficient what is it? NC n by 2. So that is n is 24. So we get 24 C 12. 24 by 2 is 12. So we get 24 C 12 is the only one largest binomial coefficient. So we shall see one more problem. Problem number 25. If P and Q, if P and Q are the sum of odd terms and the sum of even terms respectively. In the expansion of x plus a whole to the power of n, then prove that we have two bits in this one. Again, the first bit is p square minus q square is equals to x square minus a square whole to the power of n. And then the second bit is 4pq is equals to x plus a whole to the power of 2n minus x minus a whole to the power of 2n. Look at the question we have. If p and q are the sum of odd terms and sum of even terms respectively in the expansion x plus a whole power n, then prove that p square minus q square is equals to x square minus a square whole to the power of n, and the second one is 4pq is equals to x plus a whole to the power of 2n minus x minus a whole to the power of 2n. First we'll try to expand this one, x plus a whole power n. Let us see the solution. We'll try to expand x plus a whole to the power of n. X plus a whole to the power of n is equals to nc0 into x to the power of n plus nc1 into x to the power of n minus 1 into a to the power of 1 plus nc2 into x to the power of n minus 2 into a square plus nc3 into x to the power of n minus 3 into a cube plus so on plus nc n minus 1 into x to the power of 1 into a to the power of n minus 1 plus ncn into a to the power of n. Now we shall try to pair the even terms and the odd terms. So this is equals to, we'll take the even terms, say nc0 x to the power of n plus nc2 x to the power of n minus 2 a square plus nc4 x to the power of n minus 4 a to the power of 4 plus so on, and then plus nc1 x to the power of n minus 1 into a plus nc3 x to the power of n minus 3 a cube plus nc5 into x to the power of n minus 5 a to the power of 5 plus so on. So this will be equal to p plus q, because p and q are the sum of even terms and odd terms. It is given. Let us consider this as equation 1. Now we shall also expand x minus a whole to the power of n. Also x minus a whole to the power of n is equals to nc0 x to the power of n minus nc1 x to the power of n minus 1 into a plus nc2 into x to the power of n minus 2 a square minus nc3 x to the power of n minus 3 a cube, the alternate terms will be negative, plus so on, plus minus 1 whole to the power of n, ncn, a to the power of n. So this is equals to, we'll try to pay the even and odd terms. So we get nc0 into x to the power of n plus nc2 into x to the power of n minus 2 a square plus nc4 x to the power of n minus 4 a to the power of 4 plus so on, and take minus common, you have nc1 x to the power of n minus 1 into a, this minus term, and the next minus term is nc3, so will be plus, we took minus common, will be nc3 x to the power of n minus 3 a cube plus nc5 x to the power of n minus 5 a to the power of 5 plus so on is equals to p minus q. So this is equation 2. So based on these two equations, we shall prove the first and second bit. We shall prove this 2. So we shall consider the first bit. We got two equations. We shall consider the first bit. What do you need to prove? Prove that p square minus q square is equals to x square minus a square, x square minus a square whole to the power of n. Consider LHS. We have p square minus q square, which is equals to p plus q, which can be written as p plus q into p minus q. P plus q is nothing but x plus a whole to the power of n into x minus a whole to the power of n. So this is x plus a into x minus a whole to the power of n, which is nothing but x square minus a square whole to the power of n. So this we got it from one and two. Equation 1 and equation 2. So where p plus q is x plus a whole to the power of n, p minus q is equals to x minus a whole to the power of n. So what is this? P plus q is equals to x plus a whole to the power of n, and p minus q is x minus a whole to the power of n. So based on that, we got x plus a whole to the power of n into x minus a whole to the power of n, which will yield to x square minus a square whole to the power of n. So now we shall consider the next bit, second. prove that four PQ is equals to x plus a whole to the power of 2n minus x minus a whole to the power of 2n. Now consider LHS. Four PQ can be written as P plus Q whole square minus P minus Q whole square, which is equals to x plus a whole to the power of n whole square minus x minus a whole square whole to the power of n whole square. Again, this is from from 1 and 2. From equations 1 and 2. Because P plus Q is x plus a whole to the power of n, P minus Q is x minus a whole to the power of n. Now, this is nothing but x plus a whole to the power of 2n minus x minus a whole to the power of 2n. So, this is the end result. We shall see one more problem. Problem number 26. If the coefficients of four consecutive terms in the expansion of one plus x whole to the power of n are a1, a1, a2, a3, a4 respectively, then show that a1 by a1 plus a2 plus a3 by a3 plus a4 is equals to 2a2 by a2 plus a3. Now, if the coefficients, what's the question given? If the coefficients of four consecutive terms in the expansion of 1 plus x whole power n are a1, a2, a3 and a4 respectively, then show that a1 by a1 plus a2 plus a3 by a3 plus a4 is equals to 2a2 by A2 plus A3. We shall solve this one. Let us see the solution. Given that A1, A2, A3, A4 are the coefficients of four consecutive terms in the expansion of 1 plus x whole per n respectively. Let A1 is equals to NCR minus 1 A2 is equals to NCR, A3 is equals to NCR plus 1 A4 is equals to NC R plus 2. We shall continue in the next step. Consider LHS. What is the LHS we have? LHS is A1 by A1 plus A2 plus A3 by A3 plus A4. We shall consider the LHS. A1 by A1 plus A2 plus A3 by A3 plus A4 is equals to A1 as it is. In the denominator we shall take A1 common. A1 into 1 plus will become A2 by A1 plus A3 divided by, take A3 common into A3 plus into 1 plus A4 by A3. So taking A3 common, A1 and A1 will get cancelled. A3 and A3 will get cancelled. So we'll left with 1 divided by 1 plus A2 we have considered as NCR divided by A1 as, we've assumed A1 as NC R minus 1 plus 1 divided by 1 plus A4 we have assumed as NC R plus 2 divided by NC R plus 1. Next step, is equals to 1 divided by 1 plus n minus r plus 1 divided by r plus 1 divided by 1 plus n minus r minus 1 by r plus 2. So we have used the identity. We have used the identity NCR by NC r minus 1, which is equals to n minus r plus 1 by r. So now the solution, this step we shall simplify further. This will be equal to 1 divided by, in the denominator we shall take LCM, r plus n minus r plus 1 divided by r plus 1 divided by r plus 2 plus n minus r minus 1 divided by r plus 2. What are the terms getting cancelled? R and minus r, and then here r and minus r. So this will be equal to, r will go to the numerator, r divided by n plus 1 plus r plus 2 in the numerator divided by n plus 1. So which is equals to 1 by n plus 1 is common into r plus 2. So this is equals to 2r plus 2 divided by n plus 1. So which is equals to 2 into r plus 1 divided by n plus 1. Say this is equation 1. So this is equation 1. Now we shall consider the RHS and simplify that. Consider RHS. Consider RHS. So what do we have in the RHS? A2 by A2 plus A3. We shall consider this and try to simplify. Now, A2 divided by A2 plus A3, which is equals to 2A2 as it is in the numerator divided by, take A2 common, which will be 1 plus A3 by A2. So this will be equal to A2 and A2 will get cancelled. Next step, it will be equal to 2 divided by 1 plus, what did we assume as A3 NC R plus 1 divided by, and A2 is NCR. The next step, it will be equal to 2 divided by 1 plus n minus r by r plus 1, which is equals to 2 divided by, consider the LCM, r plus 1 plus n minus r divided by r plus 1. What are the terms getting cancelled? R and minus r, and then r plus 1, take it to the numerator. So we get 2 into r plus 1 divided by n plus 1. Say this is equation 2. What did we get equation 1 as? 2 into r plus 1 into divided by n plus 1. So both 1 and 2 are equal. So we can say that from 1 and 2, LHS is equals to RHS. So now from equations 1 and equation 2, we can say that LHS is equals to RHS. Therefore, A1 by A1 plus A2 plus A3 by A3 plus A4 is equals to 2A2 divided by A2 plus A3. This is the end answer. Now, you can consider that